Imagine stepping back to the mid-1950s. Computers exist, yes, but they're largely seen as, well, just gargantuan calculators.
Right, super fast number crunchers.
Lightning fast at crunching numbers, sure, but utterly blind to something we humans do effortlessly every single day.
Hmm.
Reasoning.
Mm-hmm.
Not just computing a sum, but truly thinking, making deductions, proving abstract truths, grappling with symbols and logic. What if I told you that in 1956, two brilliant minds published a paper that didn't just challenge that prevailing notion, but absolutely shattered it, like laying the very first critical brick in the long, winding road to artificial intelligence as we understand it today?
Hey everyone, welcome to Computer Science Tech Paper Summary. I'm Alex, ready to synthesize some big ideas and trace the intellectual lineage of our digital world.
And I'm Jordan, here to help us unravel the intricate logic and groundbreaking insights behind those ideas. Today, we're not just diving into an old academic paper, we're sort of time traveling.
Yeah, definitely feels like it. To a pivotal moment, a genuine paradigm shift in the history of computing. We're meticulously breaking down the logic theory machine, a complex information processing system by Alan Newell and Herbert A. Simon. This was a groundbreaking work, first saw the light of day at a symposium in July 1956, and later published by the Rand Corporation.
Okay, Rand Corp. And for listeners tuning in today, in a world that's just saturated with AI, everything from ChatGPT to self-driving cars, why does a paper from 1956 about proving logic theorems still hold such immense weight? What does it matter right now?
Well, it's foundational. I mean, truly foundational. This paper is the direct intellectual ancestor of modern AI. It wasn't just a technical achievement, it was more like a conceptual earthquake.
And it's quick. I like that.
It fundamentally demonstrated that computers could do more than just churn through arithmetic operations. They could manipulate symbols, engage in abstract reasoning, and solve problems in ways that genuinely mimicked or at least resembled human cognitive processes. So this deep dive, for you, the listener, is really your shortcut to understanding the very genesis of automated reasoning. It shows us precisely how we first dare to teach machines to think in a truly meaningful, symbolic sense. It's the origin story of so much that we take for granted in AI today.
That's a powerful statement, shattering the paradigm.
Yeah.
So let's really set the scene then. Before Newell and Simon came along with their logic theory machine, what was the established identity of a computer? What did the scientific community, the engineers, the public believe these machines were fundamentally capable of?
Yeah, it's crucial to understand that landscape, the early to mid-50s computing world. Before Newell and Simon's, radical insights, digital computers were predominantly viewed as high-speed numerical processors.
Just numbers.
Pretty much. Their forte was numerical calculation performing complex mathematical operations on quantitative data at speeds previously unimaginable. They were the champions of what was then called scientific computation, solving equations, running simulations, processing vast data sets. They were, in essence, highly sophisticated, incredibly fast slide rules or abacuses.
Right, supercharged calculator.
Exactly. While powerful, their perceived capabilities were largely confined to tasks that could be reduced to arithmetic operations on numbers. The idea of them handling abstract concepts or meaning, that was largely foreign.
Right. It was a quantitative world for computers. But as you alluded to, the real world, and especially sophisticated mathematics, isn't just about numbers. It's about ideas. It's about symbols, about the relationships between those symbols, and above all, about logic. How do you even begin to program a machine to prove a theorem, for instance? That's not just adding two numbers. That requires understanding abstract concepts like if-that-then statements, the concept of not, or the combinatorial or. This kind of problem-solving, this manipulation of abstract ideas, it just felt inherently uniquely human, like a chasm that machines simply couldn't cross.
Absolutely. That gap between numerical computation and symbolic reasoning was precisely the missing piece. And Newell and Simon didn't just intuitively sense this, they actually formally articulated what constituted a complex information processing system. They distinguished it sharply from a mere numerical calculator. They identified three crucial characteristics. First, such a system requires a large number of different kinds of processes, not just repetitive calculations.
Okay, variety.
Second, the application of these processes isn't fixed. Their use must be highly contingent, adapting dynamically based on previous operations and environmental information, essentially. The system needs to decide what to do next.
Needs to react.
Exactly. And third, these processes must be flexible, used in many different contexts, often organized hierarchically, iteratively, and even recursively. This was a blueprint for a machine that could adapt and reason far beyond anything previously conceived.
So it's not just about raw computational power, but about the flexibility and adaptability of the operations themselves, using different processes in different ways based on the context. That sounds incredibly challenging to program, especially back in 1956 when programming was still, well, pretty new.
Oh, it was a monumental challenge. And it directly contrasted with the rigid, fixed-step algorithms that dominated the computational landscape of the time. This leads us to another fundamental distinction they made between traditional systematic algorithms and what they termed heuristic methods. A systematic algorithm guarantees a solution by exhaustively checking every single possibility. For simple problems, it's reliable. But for the kind of complex tasks they envisioned, like theorem proving, it's simply not practical. It runs into what we call a combinatorial explosion.
You've hit on the critical point there, the combinatorial explosion. It's like, imagine trying to find the perfect move in chess, not by strategizing, but by mapping out every single possible future game from the very first move to the very end.
Impossible.
Even with a modern supercomputer, that would take billions, maybe trillions of years.
Yeah.
It's computationally impossible to exhaust every single possibility.
Yeah.
You don't need just speed, you need something else, something smarter, something that doesn't check every single option, something that takes shortcuts, guided by, well, intelligence.
Precisely. The paper makes this distinction explicitly and articulates the core problem they were trying to overcome. They referred to the traditional approaches as systematic computational processes, our algorithms, and their revolutionary new approach as heuristic methods. This wasn't just a technical tweak, it was a fundamental shift in thinking about how machines could solve problems, moving from guaranteed but often impossible paths to probable but efficient ones. So given this understanding of the limits of purely numerical algorithmic machines, the need for this research was, well, pressing and clear. For problems like theorem proving, which are inherently symbolic and combinatorial, the brute force systematic algorithm approach was just utterly bottlenecked by computational feasibility.
It just wouldn't work.
Right. The paper powerfully highlights this. Even for moderately sized problems, the very large number of valid chains to explore made systematic enumeration computationally infeasible.
Yeah.
This wasn't just an inconvenience, it was the critical barrier preventing computers from tackling anything beyond pure arithmetic and simple logical operations. The universe of possibilities was just too vast for exhaustive search.
So it's like trying to find a specific, perfectly formed snowflake on a vast Antarctic ice sheet by examining every single ice crystal you'd never finish.
Exactly.
It's a beautifully stark illustration of why brute force, for many real-world problems, simply doesn't cut it. And this is where Newell and Simon, as psychologists and computer scientists, look to a different kind of problem solver, us, humans. They observed that humans, when faced with these kinds of complex problems, don't use brute force, do we? We use rules of thumb, intuition, educated guesses, experience what they termed heuristic methods. Think of a master detective like Sherlock Holmes. He doesn't investigate every single person in London to find a culprit. He uses clues, patterns, experience, and a brilliant knack for inference to narrow his focus dramatically.
Right. He's not checking every alibi.
Exactly. He's not guaranteed to find the killer on his first try, and he might even make a few wrong turns. But his approach is incredibly efficient and often successful. That's a heuristic in action. It's a smart shortcut, a guided search, not a guaranteed, exhaustive path. It prioritizes finding a solution, a good enough solution maybe, over finding the perfect one through an infinite search.
That's a perfect encapsulation. The motivation for their work wasn't just about building a better computer, it was to specify and empirically study complex information processing systems that could tackle genuine problem-solving human tasks. This wasn't merely about mimicking human behavior in a superficial way, but about understanding the underlying structure of these complex cognitive processes, how we humans use those rules of thumb, and then formalizing them for a machine. This paper, presented at the legendary 1956 Dartmouth Summer Research Project on Artificial Intelligence, a pivotal moment often cited as the official birth of the field of AI, was a groundbreaking work, a direct response to the limitations of existing computational paradigms. They were explicitly attempting to move computing beyond simple calculation into the realm of structured, goal-oriented reasoning.
All right, so they identified the monumental problem. Computers were masters of numbers, but utterly lost in the world of symbolic reasoning. They articulated a critical need. Brute force doesn't scale, so we need human-like heuristics. Now, let's get into the heart of it. How did they actually build this groundbreaking machine, this logic theory machine, or LT? What did it look like inside?
Okay, so the paper specifies the logic theory machine, or LT, as a complex information processing system designed with a singular, ambitious goal: to be capable of discovering proofs for theorems in elementary symbolic logic. And the crucial design principle they stated up front was that it would rely heavily on heuristic methods similar to those that have been observed in human problem-solving activity. This wasn't just a claim, it was the core of its architectural philosophy. It wasn't a calculator, it was designed to be a theorem prover.
A theorem prover, got it.
Now, to fully specify the system, they didn't write it in raw machine code right away. Instead, they developed what they called logic language, or LL. Yes, LL. This was a formal language, sort of a pseudocode, specifically designed for human thinking or communication about complex systems. It was explicitly described as comprehensible to humans. Think of it as a meticulously detailed architectural blueprint, outlining every logical component and process before construction even began. This was critical for making their complex ideas explicit and testable, allowing them to iterate on the design before committing to the, well, arduous task of coding it for a physical machine.
So it's like writing down a completely unambiguous recipe before you even step into the kitchen. Every ingredient, every step, every decision point is crystal clear and human readable, ensuring that when you do start cooking, you know exactly what you're making and how it should work.
Exactly, a perfect analogy. And the foundational elements, the building blocks of this recipe, were called information processing systems, or IPS. And IPS fundamentally consisted of two main components: memories and information processes, IPs.
Okay, memories and processes. Sounds familiar.
Right, but for an audience familiar with modern computing, memories here aren't just generic RAM. They're specifically structured storage for information over time in the form of symbols. They define two main types. First, working memories. These were like the scratch pads or whiteboards on your desk, temporarily holding active information or expressions during a proof step, much like a human might jot down intermediate calculations. They were referred to by simple identifiers like X, Y, Z, or 1, 2, 3.
Okay, like short-term memory.
Kind of. Then there were storage memories. These were more permanent repositories holding lists of logic expressions. Crucially, this included the theorem list.
The theorem list.
Yes, which stored axioms, the fundamental starting truths, and any theorems LT had already successfully proven. This theorem list was a nascent form of cumulative learning, allowing the system to build its knowledge base over time. It also had active and inactive problem lists, dynamically managing its current and pending tasks.
So, a highly specialized memory architecture, designed specifically to manage the symbols and problems of logic. Makes sense. And then you have the actions that interact with these memories. The information processes. What did those look like? Were they complex?
The information processes, IPs, were the real muscle, the elementary processes that acted on these memories. Mathematically speaking, they were functions taking symbols from input memories and producing symbols in output memories. But what's truly revolutionary here is the granularity and symbolic nature of these operations. Newell and Simon broke down something as abstract as thinking or logical deduction into 44 distinct elementary steps.
44. Wow.
Yeah, but they were built from just 8 fundamental operation types. And these weren't about arithmetic operations like adding or multiplying numbers, not at all. They were about symbol manipulation. Things like assign for naming and locating elements, branch for controlling the flow of execution based on conditions like an if statement, compare for checking if two symbolic expressions were identical, find for searching storage memory for specific patterns or expressions.
Okay, finding things in memory.
Right. And put and store for moving symbols between different memories, working memory to storage, or working memory to working memory. And finally, test for checking properties of elements, like if an expression was a unit or a specific logical form. This showed that complex logical operations could be constructed from a surprisingly small, finite set of simple, symbolic building blocks.
That's fascinating. It really underscores their insight. That thinking at its core could be broken down into discrete, formalizable actions on symbols. So you have these basic symbolic actions, these IPs and specialized memories. How do they combine to actually do something meaningful, like construct a proof?
That's where programs and routines come into play. Individual IPs were combined into routines. These were sequences of these elementary instructions with control flow, meaning they could branch based on conditions, make decisions. The paper even imposed specific structural restrictions on these routines to manage complexity. Like, they stipulated routine should contain no more than 2 branches and refer to no more than 3 working memories outside the routine itself.
So keeping things manageable, modular.
Exactly. This hierarchical organization was key. It allowed complex problem-solving tasks, like proving a theorem, to be broken down into simpler, manageable subroutines, each performing a specific part of the overall logical process. It's a very structured, modular approach to building complex, intelligent behavior from simpler, verifiable parts.
Okay, this is where it gets really interesting for me because this is where LT truly shines, right? Mimicking human ingenuity and moving beyond just brute force calculation. These aren't just any old algorithmic steps. These are smart methods, heuristics that guide the search for proof. The paper describes three main heuristic proof methods. Let's start with the first one, the substitution method. What's that about?
Right, the substitution method, or MSB. At its heart, it's about finding structural similarity. LT attempts to prove a target theorem by searching its theorem list. Remember that list of known truths?
Yep, axioms and proven stuff.
It searches that list for an axiom or an already proven theorem that is similar in its general structure to the one it's trying to prove. If it finds a similar one, it then tries to make the known theorem identical to the target theorem by legally substituting variables and replacing logical connectives. It's not a blind trial and error, though. The system uses cues from the target expression to intelligently limit its search for suitable substitutions.
Okay, let me try an analogy. Imagine you have a complex jigsaw puzzle. You're trying to fit a specific piece you need into an empty space. Instead of searching every single piece in the box, which would be brute force, you spot a piece that looks almost right. It has the right shape overall, maybe the right colors on one edge. And you think, okay, if I just swap out this variable, or maybe replace this and with an or rotate it slightly, metaphorically speaking, it would fit perfectly. That's substitution, right? You're trying to morph a known truth into the new truth you're trying to establish.
That's a great way to put it. You're morphing based on similarity.
So how does LT actually execute that kind of morphing? What are the mechanics?
It's a multi-step process involving specific routines. Key routines involved here include CSM, which stands for check for similarity between expressions. That's the first step, find a likely candidate. Then there's LMC, a matching routine that methodically identifies corresponding parts of the two expressions, figuring out which variable corresponds to which connective might need changing. Finally, LSD executes the actual substitution routine, making the changes. The paper gives an example. Proving the expression P implies not P implies not P. LT works backward from this expression, looking for known truths it can transform. It might, for instance, consider axiom 1.2 from Principia Mathematica, which is P or not P, a basic logical tautology.
Right.
By substituting not P for P in this axiom, and maybe changing the connective, it tries to arrive at the target expression, guided by the structural cues. It's a very elegant way of leveraging existing knowledge.
That's incredibly elegant for a machine of that era.
Yeah.
It really captures a very human way of thinking about logical deduction, finding parallels and making adjustments. Okay, that's the substitution method. Very cool. What's the second ingenious method they devised?
The second is the detachment method, or MDT. This method is basically a direct computational implementation of a classic rule of inference known as modus ponens.
The modus ponens, okay. The if P, then Q, P, therefore Q rule.
Exactly that. If LT wants to prove a particular expression, let's call it A, it searches its memory, its theorem list, for two other expressions. First, an axiom or already proven theorem, let's call it B. Second, another theorem that states B implies A. If it successfully finds both of these premises, both B and B implies A in its theorem list, then A is proven as a direct logical consequence. It can detach the A.
Ah, this is a classic logical leap.
Yeah.
If you know if it rains, the grass is wet is true, and you also know it is raining is true right now, then you can detach the conclusion. The grass is wet. It's an automatic inference. You're taking established truths and seeing what new truth automatically, logically just falls out from them. This truly starts to feel like a machine reasoning in a very fundamental way.
Precisely. And again, crucially, this isn't a brute force search through all possible implications. This method also employs heuristic devices that select particular theorems. The B and B implies A rather than blindly searching through every single axiom or proven theorem in its memory. It looks for promising candidates. The paper provides the example of proving theorem 2.06 from Principia Mathematica. P implies Q. Any Q implies R. Therefore, P implies R, basically transitivity of implication.
A chain of reasoning.
Right, a form of hypothetical syllogism. LT would likely use two detachments here. It might first find P implies Q and another theorem that implies P implies Q P implies R. Then it combine that derived result, P implies R, perhaps with another theorem, P implies R implies P implies R maybe, to reach the final conclusion. It's all about efficiently navigating known logical pathways.
Fascinating. So you're not just looking for a structural match, like in substitution. You're looking for a direct logical inference, a conclusion that must follow if the premises are true. Okay, so with substitution and detachment, LT already has two powerful arrows in its quiver. What was the third strategy they envisioned?
The third method is the chaining method, or MCH. This is primarily used to prove implications, specifically expressions of the form A implies C. Instead of directly proving A implies C from scratch, LT tries to find an intermediate expression, let's call it B, such that two things are known or can be proven. First, A implies B is true, and second, B implies C is also true. If such an intermediate B can be found, then by the transitivity of implication, A implies C is proven. It's like finding a stepping stone.
Oh, okay.
And what's powerful about chaining is that it can work both forward, starting from A, and trying to find a path or chain leading to C, or backward, starting from C, and trying to find a chain back to A.
This is like building a bridge with multiple segments. If you know you can get from point A to point B, maybe using one theorem, and then you know you can get from point B to point C using another theorem, you've effectively built a chain, a logical path from A all the way to C. It's about connecting the dots, or rather, connecting the propositions to form a continuous line of reasoning. This method really highlights the combinatorial nature of logical proofs, finding that path.
It absolutely does. The paper illustrates this with proving a simple but fundamental theorem like P implies P. While it seems trivial to a human, the chaining method can establish this by linking known theorems. For example, it might use an intermediate expression like P or P, which implies P, and perhaps another axiom to build a chain of implications that ultimately lead from the starting P back to the ending P. All three of these methods, substitution, detachment, and chaining, are explicitly heuristic. They don't guarantee finding a proof every time, but they use intelligent cues, structural similarities, and establish logical rules to guide the search. This vastly reduces the computational effort compared to any systematic exhaustive search. They prioritize efficiency and probable success over absolute guaranteed completeness.
So we have these three incredibly smart strategies: substitution, detachment, and chaining, each designed to tackle different aspects of logical proof with something like human-like efficiency. But who's in charge? Who decides which strategy to use, when to apply it, and how to coordinate all these different problem-solving attempts? There must be a manager, right?
There absolutely is. That pivotal role falls to the executive routine, or X. Think of it as the master controller, the central nervous system, and maybe the strategic conductor of the entire LT system.
The conductor, I like that, waving the baton.
Exactly. Its primary function is to oversee and coordinate the application of these three heuristic proof methods. It's the one that decides, based on the current problem and available resources, which method to try next. And crucially, the executive routine identifies and manages subsidiary problems. These are essentially smaller theorems that need to be proven as intermediate steps to achieve a larger proof.
Like sub-goals.
Precisely. For example, if the detachment method requires proving B before it can prove A, then proving B becomes a subsidiary problem that X adds to its workload. It has to manage these dependencies.
That's fascinating, a very human-like way of breaking down complex problems. We often do that instinctively, seeing a big goal, then identifying the smaller steps or prerequisites needed to achieve it. So it effectively creates a hierarchy of problems.
Exactly. The executive routine actively maintains a problem list, distinguishing between active problems it's currently working on and inactive ones it might revisit later. This allows it to manage its focus and not get bogged down. But here's another critical innovation for its time. X incorporates stop rules.
Stop rules, like knowing when to give up.
Sort of. They are global constraints designed to prevent the program from getting lost in computationally exhaustive or unproductive searches. These rules are vital. They prevent LT from duplicating efforts unnecessarily. They limit the amount of work applied to any single problem, often measured by a cumulative tally or some index of the amount of work expended.
Okay, a budget for thinking time.
Exactly. And they terminate routines if a proof isn't found within reasonable, predefined limits. Without these stop rules, the efficiency gains of heuristics could quickly be lost to unbounded, albeit smart, exploration. You need some practical limits.
That makes perfect sense. You don't want your brilliant heuristic-guided program to get stuck in an infinite loop or to spend an eternity chasing a proof that might not even exist or just isn't worth the computational cost at that moment. The practical constraint on what it considers intelligent use of resources.
And here's where it gets even more intriguing in terms of early AI capabilities, something truly forward-looking for 1956. The executive routine also manages a simple but remarkably powerful learning mechanism.
Learning. In 1956, how?
Well, whenever LT successfully proves a new theorem, X stores that newly proven theorem in its theorem list within memory.
It adds it to the known truths.
Exactly. These theorems then become available as building blocks, essentially as new axioms, for solving subsequent problems. This allows the program to accumulate experience, to expand its knowledge base over time. This is a critical, albeit simple, form of machine learning. It demonstrated that the system could improve its performance and efficiency as it encountered and solved more problems. It wasn't just solving a problem and forgetting the answer, it was actively building its expertise, adding tools to its toolbox.
Wow. Okay, that is learning. Basic, maybe, but definitely learning, storing results to use later. That's huge.
So, what did all this intricate design, this sophisticated approach to symbolic logic and heuristic problem solving, actually yield? What were the results? The key findings and results from Newell and Simon's logic theory machine were, well, nothing short of revolutionary. They proved their ambitious theoretical framework could actually be realized. First and foremost, LT successfully demonstrated that complex logical proofs, previously thought to be exclusively in the domain of human intellect, could indeed be achieved by a machine using heuristic methods. This was a profound, undeniable proof of concept for the feasibility of machine intelligence.
So step one, show it can be done. Check.
Right. And this wasn't just a theoretical win, it was an efficiency triumph over brute force, which is what truly astonished the computer science community at the time. The paper highlights this dramatically with an almost unbelievable statistic for a specific problem they analyzed, where a systematic search, that's the brute force approach, might require examining upwards of 10,104 potential proof chains of just 4 steps.
10,000 possibilities.
Yeah.
LT, guided by its clever heuristic cues, typically only examined a mere eight chains.
Wait. From 10,000 down to 8?
Yes.
Jordan, that's not just an improvement. That's an astronomical leap in efficiency for complex problems. We're talking about reducing the search space by a factor of over 1,000, potentially even more sometimes.
It's incredible.
It's like finding that proverbial needle in the haystack in minutes instead of years. It completely changed the game for how computers could approach intricate tasks. It proved that intelligence isn't just about raw speed, but about smart shortcuts. It was the first undeniable evidence that heuristics could unlock computational power in ways brute force never ever could.
It is truly staggering, a testament to the power of guided search. And this wasn't merely a theoretical demonstration on one hand-picked problem. The system was empirically tested on actual theorems from Chapter 2 of Whitehead and Russell's monumental Principia Mathematica.
The Principia, that's like the Mount Everest of symbolic logic.
It's certainly a major peak, and LT proved an impressive 38 of the 52 theorems in that chapter, and an additional 12 from later parts of the book. This showcased its robust, practical capability. This was no toy. It was a functioning, reasoning machine successfully tackling a significant portion of a highly respected, notoriously difficult mathematical text.
Okay, so this isn't just a conceptual breakthrough. It's a verifiable working system that's getting real results on hard problems. This paper fundamentally changed what people believed computers were capable of doing. It showed that machines could not only perform arithmetic, but also manipulate symbols and engage in abstract reasoning. This directly led to the birth of the field we now call artificial intelligence. This was the moment the idea of a thinking machine started to move decisively from the realm of science fiction into demonstrable scientific reality.
And that learning aspect we discussed, the executive routine storing proven theorems, that was absolutely pivotal to this success.
The cumulative knowledge.
Exactly. The program's ability to store previously proven theorems in its theorem list and then reuse them as new axioms for subsequent proofs constituted an early yet powerful form of machine learning. The paper explicitly states that without this cumulative knowledge, it is doubtful whether the program would prove any but the first few theorems of Chapter 2 in a reasonable number of steps. This accumulation of experience, this rudimentary form of memory and reuse, was fundamental to its overall performance. It demonstrated that machines could indeed learn and improve their problem-solving capabilities in a meaningful, if constrained, way.
Okay, so LT was a monumental achievement, a genuine watershed moment. It proved machines could reason efficiently using heuristics and even learn in a basic sense by remembering successes. But, with any groundbreaking research, it's equally important to examine its edges, its boundaries. What were the inherent limitations of the logic theory machine? What critical reflections did Newell and Simon, or maybe subsequent researchers, offer?
That's a crucial point, and it reflects the scientific rigor of the paper itself. They were aware of the trade-offs. One of the primary limitations, inherent in its core design philosophy, is that while heuristic methods are incredibly powerful and efficient, they offer No guarantee of finding a proof.
Right, the shortcut might not always work.
Exactly. They significantly increase the probability of finding one efficiently, but they don't promise it will always succeed, unlike exhaustive, systematic algorithms which, if they finish, are guaranteed to be correct. This is a fundamental trade-off. You gain immense efficiency, but you lose certainty. It's akin to a human trying to solve a complex puzzle. You might use smart strategies, but you're never absolutely guaranteed to find a solution, or maybe even the optimal solution. Sometimes good enough has to be good enough.
So it's a brilliant shortcut, but sometimes a shortcut might lead to a dead end, or there might be an even better undiscovered path that the heuristics simply don't consider. It forces us to ask, what does intelligence mean if it's not always perfect or complete? Does it have to be?
Exactly. It forces a reevaluation of that very definition. Another important point, sometimes overlooked in the excitement surrounding the results, is that this particular paper primarily focuses on the specification of LT in logic language. LL. Remember the pseudocode?
Ah, right. The blueprint, not the finished building.
Pretty much. It wasn't about its complete deployed realization on a physical computer in this specific publication. While the detailed blueprint was laid out and shown to be logically sound, the actual coding and full implementation on a digital computer, primarily the Joniac at Rand, would follow shortly after. That work was spearheaded by Newell, Simon, and their colleague J.C. Shaw. So this 1956 paper was the detailed plan, rigorously argued, but not yet the fully functioning machine at the exact moment of this paper's release.
Okay, that's an important clarification. And what about that learning capability you mentioned? It was impressive for the time, but was it truly intelligent learning as we might understand it today, with systems that adapt and generalize across vast domains?
Well, the learning in LT was quite specific and constrained. It involved storing newly proven theorems as facts, which then became available as axioms for subsequent proofs. This was immensely powerful for its specific task theorem proving. However, it wasn't about the system generating new heuristics or fundamentally changing its own problem-solving approach in a meta-learning sense. It couldn't invent new ways to prove things.
Oh, okay.
It could expand its knowledge base of facts, its library of theorems, but it couldn't learn how to learn better or devise completely novel strategies for reasoning. The core methods, substitution, detachment, chaining, were fixed.
So it could learn new facts within its predefined rules, but the rules of the game, the heuristic methods themselves, were still hard-coded by the human designers. It highlights that even at this early stage, the machine's autonomy was deeply rooted in human-defined structures and limitations.
Precisely. Furthermore, the paper itself is quite modest in its claims about broader significance. It intentionally abstained from comment on the more general significance of the ideas and techniques introduced. It was presented as a highly focused empirical study, rigorously demonstrating a system for a specific problem, a symbolic logic theorem proving. It was not presented as a grand philosophical treatise on universal intelligence or complex information processing in general.
So no sweeping claims about having created thinking in general.
No, it was a precise scientific investigation into one type of intelligent behavior, not all of it. This measured approach reflects the careful scientific method of its authors, even while they were clearly breaking incredibly new ground.
And speaking of human input, the system still relied heavily on humans, right? To define the initial axioms, to define the very logical framework it operated within, it didn't invent its own logic or decide what fundamental truths were important.
That's a crucial distinction. LT demonstrated how a machine could apply reasoning principles within a defined framework. It expertly applied the rules of logic that humans, over centuries, had painstakingly developed. It didn't, and frankly wasn't intended to, discover those principles from scratch or define its own domain of knowledge or, say, a moral framework.
Right.
It was a brilliant tool for exploration and proof within a given system, but still very much a sophisticated tool guided by human design and pre-programmed logical structures. This human-in-the-loop aspect for defining the foundational knowledge and the very rules of the game would remain a significant challenge and maybe a feature for symbolic AI for decades to come.
So if that was the state of affairs back then, these groundbreaking achievements tempered by their inherent limitations, what kind of doors did this paper truly open? What future directions did it suggest? How did it influence the trajectory of computer science and the brand new field of AI?
Well, the immediate future, as we briefly touched upon, was the actual coding and full implementation of the logic theory machine on digital computers, getting it off the page and onto the hardware, primarily the Joniac machine at Rand. This was achieved shortly after this paper's publication by Newell, Simon, and Shaw, demonstrating that the logic language specification could indeed be translated into a working program was a critical validation. It showed the blueprint was buildable.
And once it was a real functioning piece of software, the imagination must have absolutely exploded. I mean, if a machine can prove theorems using these heuristic methods, what else can it think its way through? Could these same approaches, these clever shortcuts, be applied to other complex human-like problems beyond just symbolic logic? Like, could it play games, chess or checkers, which involve deep strategic reasoning and heuristics?
Exactly. That was a natural next step.
And this eventually led to the development of the general problem solver, right? Also by Newell and Simon, which aimed to tackle a much broader class of problems using similar means-ends analysis heuristics. You start to wonder about things like medical diagnosis, financial analysis, or even just everyday planning, like figuring out how to get across town. The possibilities just begin to multiply once you see reasoning can be automated.
They absolutely did multiply. And that simple learning process in LT, the storage of proven theorems, was just the tip of the iceberg conceptually. It opened the door to much more advanced machine learning paradigms. Systems where machines could indeed adapt, generalize, and even discover new strategies or refine existing heuristics over time. This humble beginning sowed the seeds for adaptive AI, demonstrating that knowledge accumulation was a powerful mechanism for improving system performance. Future research would explore how machines could learn not just facts, but new rules or patterns of reasoning itself.
And beyond just the technical advancements in computer science, you mentioned Newell and Simon had psychology backgrounds. This work also had profound implications for our understanding of human cognition itself, didn't it? Blurring the lines between disciplines.
That's a critical point, yes. This work profoundly influenced the emerging field of cognitive science. Newell and Simon saw this as more than just computer engineering. They saw it as providing a computational framework for how the human mind might process information.
A model of the mind.
A testable model, exactly. How we might solve problems, structure our own memory, and maybe even learn. It offered a testable, formalizable model for aspects of human thought that were previously just described vaguely. It connected computer science directly to psychology and philosophy. It essentially made the inner workings of human reasoning seem more accessible and formalizable, moving it from fuzzy intuition toward potentially concrete, symbol-manipulating processes.
It's incredible to think about how far-reaching the influence of this single paper truly was.
Yeah.
This isn't just some dusty historical footnote. This is the intellectual grandparent of so much that followed. Everything from automated planning systems and the expert systems that were huge in the 70s and 80s
Definitely.
to maybe even the underlying logic and symbolic manipulation that informs certain aspects of modern large language models today, even if they work very differently overall. It truly set the stage for decades of what was known as symbolic AI, or sometimes good old-fashioned AI, GOF AI.
It absolutely did. It taught us that intelligence isn't just one monolithic, mystical thing. It's likely a collection of processes: memory, comparison, branching, substitution, detachment, chaining, planning, learning. And many of those processes, even the ones we might consider intuitive or creative in humans, can potentially be formalized and executed by machines through symbol manipulation. It gave us a concrete roadmap, or at least a first draft, for dissecting and potentially rebuilding aspects of intelligence, one heuristic at a time. It forever altered the landscape of computing and the very definition of what a machine could possibly achieve. All right, let's try and boil this down. The TLDR for you, the listener. The Logic Theory Machine by Newell and Simon, presented back in 1956, was fundamentally a groundbreaking demonstration. It showed that computers could use human-like heuristic methods, think smart shortcuts and rules of thumb, to efficiently solve complex symbolic logic problems like theorem proving. This was a radical departure from the computationally infeasible brute force algorithms of the era, which just couldn't scale. This seminal work didn't just pave the way for artificial intelligence, it fundamentally redefined the potential of computing beyond mere numerical calculation and pushed it firmly into the rich, abstract realm of reasoning and symbolic thought.
Okay, so here's a final thought to chew on. You, the listener, solve problems every single day with heuristics. Gut feelings, educated guesses, rules of thumb you've picked up through experience, maybe without even thinking about them consciously. Think about one such problem you face regularly. It could be anything: navigating a new route in traffic, debugging a tricky piece of code, or even just deciding the most efficient way to run your daily errands. How might you articulate your own intuitive heuristics for that problem? Could those human insights, those smart shortcuts you use almost automatically, could they be codified, written down clearly enough for a machine? That's the very challenge Newell and Simon tackled back in 1956 with logic. And it's still a fascinating, open-ended question today that underpins so much of what we continue to explore the field of AI. How do we capture and automate that flexible, efficient, heuristic intelligence? That's our deep dive into the logic theory machine. I'm Alex.
And I'm Jordan. Thanks for joining us on Computer Science Tech Paper Summary. Keep on diving.